I mean, you want to just introduce yourself, Matt?
Sure.
Most people probably, you gave us several talks over the years, so a lot of the
Is
Toronto folks will probably know you, but feel free to introduce yourself, and thanks for being here.
all right. For those that don't know me, I'm Matt Trudel. I'm a Torontonian Elixir developer. I've done a couple of talks at the meetups over the past couple of years. A lot of them have had a sort of a bias towards more embedded work or more sort of like lower nuts and bolts work. And this is no exception. So you might notice in the background, it looks like you're in my basement. It's because you are. So I'm actually at my workbench right now because this is actually going to be a hands-on talk. We're going to be talking about nerves today. So I apologize. There's some live showing hands thing here. I'm going to be moving the camera around a few times, so apologies if things get nauseatingly movie, but it's the best I can do. And also, please do let me know if the AV turns off and you don't actually see something that I'm talking about, because I'm kind of flying blind here with the way my screens are set up. So the quick agenda for today is a quick intro to what nerves actually is. We're going to talk about a Hello World program with it. I'm going to demonstrate how nerves allows you to use Elixir to interact with real world things like buttons and LEDs. I'm going to show some examples beyond just simple buttons and LEDs, various things you can do with it. And I'm going to actually demo a fairly feature complete desktop clock application written in nerves. So first off, what is nerves? If anyone hasn't heard of it, it's a framework for running Elixir in embedded environments. So what this basically means is that it's a toolkit that handles cross-compilation, packaging, building and packaging firmware for a bunch of different platforms and a bunch of other details that go along with that. It has some device-side tooling for letting you interact with bits and bobs on the various devices that you talk to. And it's all run by essentially implementing the Beam on top of a really small Linux distro. It's based on a tool called Buildroot, which if anyone here has done any embedded work, Buildroot is sort of a grounds. It's a very foundational framework that a lot of embedded systems and embedded applications use to target Linux at various embedded devices. So in theory, Nerves runs on any of them. For the most part, the vast majority of people use it on Raspberry Pis and BeagleBone Blacks. So if none of this really makes any sense to you, you can essentially just think of it as Elixir running on a Raspberry Pi. And if anyone's never seen a Raspberry Pi before, so now is when the AV gets tricky here. Hopefully you guys are seeing my hands right now. Mattia, can you? You're the only person
as your camera, yes, as
yes,
your
great.
camera.
Okay,
Yes.
lovely. Sorry, I'm flying completely blind here on my screen. So a Raspberry Pi is this small little computer. They cost, in theory, $5. That's American. In reality, they're more like $10 by the time you get them shipped. Runs Linux, has a USB port, an HDMI port, boots off an SD card, and it has a number of other GPIO pins here on the top that you can use to interact with things in the real world. So I've taken one of these and I've wired it up in this handy dandy board here to an LED and to a button. So the LED is wired up to a pin so that we can turn it on and off, and the button is wired up to another pin on the GPIO so that we can see it be pressed. So if we're actually going to go and start a Hello World version of this, the first thing we need to do is install Nerves. I'm actually going to skip over this part, partly because it varies from platform to platform. The instructions are different depending on the platform you're on. Second, because the Nerves project, as they do with most of their documentation, their documentation on installation is really superb. And it does change a little bit as the project's sort of in flux. So I will go through this. It's nothing hugely difficult, but it's just not something I want to spend time on. Very well documented. I will say one thing about it. In a number of places in the documentation, they refer to installing particular versions of OTP and particular versions of Elixir. You can try to think you can try to be clever and think that you know better than they do with those things, but oftentimes if you don't, those will come back much later in the process when you're actually trying to get this stuff running on a device. And the error messages that pop up at that point will be fairly instructive about what to do in terms of going back and updating your OTP, but you almost certainly will have to go back and do that. So it's usually easiest to just listen to their instructions unless you certainly know what you're doing. Step 2, creating a new project. So this is fairly straightforward for anyone. This looks like the usual process for running just about any new project, Phoenix or Elixir or otherwise, or Mix or otherwise. And so we're actually going to run through that right now. So we're going to go mix nerves.new hello nerves. And this is going to go out and build your usual standard template application. It is a bit slow because my machine is older than the hills. So don't get the wrong impression about the general speed of Elixir. Just get the impression that I need a new laptop. Great. Then I will go into hello nerves. And if you look at the directory structure here, it's pretty straightforward. It's the usual thing that, well, maybe deps is maybe not the best way to do it. If I go and look at what's in your library, it's got the standard config file, your standard setup there, your standard libs application. It's in every way, shape, and form a standard mix application. That just happens to have a number of dependencies in its depth file. These are all the nerves dependencies. It has some that are generic in terms of the nerves project and some tools that it uses on the device. It also has dependencies for specific targets. So we'll talk about targets in just a moment, but this is essentially a bunch of different nerves packages that are in place for various targets depending on what type of device you want to talk to. So for the purposes of our demo, I'm going to add one line to this, which is the circuits GPIO library. This just allows us to talk to the GPIO pins on the Raspberry Pi. I will come back out. I will run a mixsteps.get to pull that in. And I will run then mix target equals rpi0 mix firmware.burn. So just to break this down, you're passing in a mix target equals rpi0 here. This is the first time that we're actually telling telling nerves which particular type of device we want to. I should probably put my SD card in my computer. There we go. This is the first time that we're really telling nerves which type of device we're building for. So at this point, it's taking that project, it's going and building a version of it that targets the Raspberry Pi Zero. And because we called firmware.burn, instead of just firmware, it actually is taking that and burning it onto this SD card. So it will go and compile the entirety of the project, which again, will take a while because I don't have a terribly fast computer. Excuse me. And it will then go and burn this off to an SD card. So while we wait for that, I'm just going to go back to my slides for a minute and talk about the things we can do with this. So as I showed with that mix application, this is just Elixir. There's nothing special here. You'll see in a moment we have an IEX session that actually runs on the device, and it's a standard REPL that lets you do anything you want to do in Elixir. It's standard Elixir, so you can run Phoenix, you can make API calls out to services, you can host a server, you can do whatever you'd like with this. And it can also interact with the physical world, which is what we're going to show here. So now, peeking at my password, it's now going and burning the SD card. And once this is done, we'll actually load it up inside this Raspberry Pi. We'll connect to it. And get an SSH, get an IEX session, and we'll start actually interacting with the physical world. So I just burned this SD card, taking it out and inserting it into the Raspberry Pi. And I am then taking the USB cable that goes into the Pi and touching it into my computer. So one thing that you'll notice, if anyone has used a Pi before, you'll notice that I'm actually connected to the USB port on here and not the power port. So this is actually a really cool hack. You'll notice at no point here have I actually gone and set up any networking. I'm not connected over Ethernet. I haven't configured Wi-Fi, and yet I'm still able to, on my computer, I'm still able to go SSH to nerves.local once it boots, of course. And the reason that works is because I'm connected over the USB port, the nerves application actually sets this guy up to look like an Ethernet port over USB. And so my Mac sees it as a USB Ethernet device and then sets up zero-conf networking over it. And so all of this networking, you'll notice that I'm actually attached to this IEX session here. This is actually running on the Raspberry Pi right now. And you can see, and this is just standard, you know, I can do everything that I want to be able to do here. I can, you know, run anything I'd like, but it's actually running on the device. And so what we can do with this is we can go circuits.gpio.open. We can go, which one is it? 26 for output. And then I can go circuits. So keep an eye over here on the LED, which is kind of shining up right there. Circuits.gpio.write GPIO1. I don't know if you can notice that, but I turned it on. I turned it off. Hopefully you can see that. I don't really want to get too close to it, but hopefully everyone can see that turning on and off, which is pretty neat, right? I'm running Elixir code on an IEX session that's actually pushing buttons in the real world or changing lights in the real world. So that's kind of the beginnings of what this looks like. I'm actually going to show one bit that is the kind of next step with this. Now that we've gone and showed a demo of it, we're actually going to set up the LED blinking, and we're going to actually be able to read the button. So the first thing I'm going to point out is I have set this LED up with a current limiting resistor. This is sort of a standard like circuits GPIO 101 setup. If you've never done this kind of stuff before, a really good introduction to this is the Circuits GPIO README. They have a really great introduction on basic wiring setups and how to set these things up, how to actually hook buttons up to LED and buttons and LEDs up. I would highly recommend reading this if you haven't. There's a million tutorials on the internet for this. This one's just as good as any other one. But I would definitely recommend getting into that before you really start doing stuff, because you can burn your board out if you do it incorrectly. So I'm actually going to show you another bit here, which is how to iterate on this. Now, the first time we did this, we actually took the SD card, put it in the computer, burned the firmware, brought it over to the Raspberry Pi, turned it back on. That gets slow in real development. So what we used for that, the NERS packet, the NERS folks have this really handy program, really handy library called NERS firmware SSH. And you can probably guess what that's going to do based on the name of it. But I'm going to just install that really quick. And then we're going to add a few new applications or a few new modules to our application, just to sort of demo once again that this is a sort of standard Elixir app. So we're going to define a quick little task here called Blinker. And Blinker is a task that it's implemented as a task. It starts, it does exactly what we just did, opens a GPIO pin for output, and then it just recurses on this blink call that writes the pin high to turn the LED on, waits half a second, writes the pin low to turn it off, waits half a second, and then just tail recurses on itself. I'm also going to add a button module, which is a gen server, which opens up, once it formats here, opens up a pin for input, sets some parameters so that we get messages whenever the pin the pin that we're talking about the circuit is opened and closed, and those set interrupts causes those to come back with these handle info calls, one when the button is pressed and one when the button is released. And we'll just log out messages when that happens. You might notice that this is kind of inverted. The button press is 0, causes the button to go, the pin to go to 0, and releasing it causes it to go to 1. That's because we use what's called a pull-up resistor for that. This again is covered by the Circuits GPIO intro to circuits. This is just know that this is, if you've never seen it, this is a very standard way of setting up GPIO. So then we will add those two, hold on, hello nerves.blinker and hello nerves.button. We will add those to our application tree. We will go and run mix firmware to build the firmware. One thing I will point out here, the next command that we're going to use is from the Nerves SSH program module package. It's the upload command. It does not build your firmware, it just uploads your firmware. So if you are iterating on this, you do need to do your mix firmware step separately from your mix upload step, which is what we're going to do as soon as this builds. All right. Does anyone have any questions so far? Is this an okay speed for everybody? I'm speaking clearly enough, hopefully. All right. So then the next thing we will do is a mix upload nerves.local. And when we do this, instead of pulling the SD card out and stuffing it in the computer and burning the SD card every single time, this actually goes and updates the firmware over SSH onto the device, and then automatically reboots the device for us. So this can turn your development cycle on these things around from multiple minutes and lots of fiddling and dealing with cards and ejecting them to you never actually even need to touch the device. And then so it's now rebooting, as you can see here. So in the meantime, we will go try to SSH to the device, and as soon as the device comes up, we will be able to SSH to it. And you should expect in the camera when this device starts, because that application the blinker task was started by the Mix project. You should expect to see the LED blinking, assuming I didn't typo anything. So we shall see as soon as it starts, and there, hopefully you can see that LED blinking, and we've attached to the IEX session on the Pi. So now, if I go and push the button here, hopefully you can hear this. Oh, but there's no logs coming out. So the reason there isn't is because, and it tells you right here, Ring Logger is collecting log messages from Elixir and Linux. To see the messages, attach the IEX session to the logger or print the messages in the log. So this is actually a handy little bit because this allows you to use the REPL without being spammed with log messages as things happen. When you call ringlogger.attach, you actually start attaching to them. So now you will see those log messages happen, right? So this is, a handy little bit. And if you want to go back, you can also go ringlogger.tail100, and that will log you back the last 100 log messages that you've seen. So kind of demonstrated a really quick introduction to how to do GPIO, how to bootstrap up a Nerves project from scratch using the nerves.new project command, and showed off just a quick little way using Nerves firmware SSH to be able to turn your development cycle around a bit faster. So now that we've seen that, let's talk about some other things that this can do beyond just buttons and LEDs. So there's a typo on here, physical protocols. Great. So there's a number of other physical protocols that are used in the embedded world. I2C is one, SPI is another, RS-232, the old-fashioned serial port. And a lot of these have been codified, at least in the Raspberry Pi world, into these things called HATs and FATs. And HAT stands for hardware attached on top, and FAT is, I don't know what the P stands for, but it's just smaller versions of it. And so they look essentially like this. They are small little devices that are the same size as a Raspberry Pi, and they sit just on top of the pins there and clip on and magically just work. They have an EEPROM on them that allows it to be able to tell this guy how to configure itself automatically. The majority of them just work. This particular one is a Wi-Fi adapter. The newer versions of the Pi have Wi-Fi. The first versions did not. So one of these was necessary back in the day. They have audio adapters. This one's a little DAC with a headphone jack on it. They have breakout boards that break them out into various GPIOs and little breakouts for other pins. There's a variety of these guys. There's little e-ink displays, LED boards where you can individually address a board full of RGB LEDs. They have little capacitive touch screens. There's all sorts of these. I would take a look at, there's a shop in the UK called Pimaroni, I guess. I mentioned them largely because they seem to have the best collection of these. So if you go to their storefront, you can see, all of the wide variety of what's available as hats. And just about any of them are interactable with via one of these protocols, via usually I2C or SPI. And there's libraries to interact with those from within the circuits GPIO and the circuits SPI libraries and a number of other NERS libraries. And those interactions all look pretty straightforward. There's a number of local sites. BioPi is obviously based in Canada. They are a local shop to be able to buy the stuff if you don't feel like waiting for the stuff from Pimaroni. There's a number of other shops as well online that sell this stuff. So as a demo for this, I'm going to show off, this is a little device that I made kind of as a joke at work. I've been working on it, formalizing it over the past few months in preparation for this talk. It provides an NTP synced desktop clock. So one of the nice things about the fact that Raspberry Pis run Linux is they can run NTP, so they can network time sync. And of course, there's a NERS package that's built in that's optional to be able to do this, that tracks your NTP synchronization status. And in this case, I use the NTP time to power an SPI connected OLED display, which looks like this. It's a small little OLED display. It's got some pins on it. And this gets wired up to a Raspberry Pi, just using a bunch of header wires that jump back between them. It's a standard Elixir app that uses circuits SPI and circuits GPIO, which are, I showed you circuits GPIO already, and some extra little bits. And essentially what it does is builds this guy. So this is where it might get a bit nauseous. So I have this hidden up here because if I don't, which way is right? Hold on, there we go. If I don't, there we go. So this is a little clock. I just threw it inside a simple little 3D printed case. And it just shows the correct time in ETC and UTC. It has a little rotary encoder dial on the top that when you turn it, changes the time on the top and cycles through a number of pre-configured time zones. If you hold it down and turn it, it changes the bottom time. And if you tap the button, it turns the display on and off. So this is powered entirely by nerves. And it's literally just a Raspberry Pi Zero, one of those little devices that I just showed you, those OLED displays, and some code that I want to walk through now to show you. So it's based primarily on, there's really not a whole lot to the desk clock project itself.
Matt, for the camera went off focus, so we're seeing.
Oh, hold on, yeah. I don't actually think I have any more camera-based stuff, but just so it isn't so nauseating. Is that better? Great.
Yeah, or you can go back to the face, whatever you prefer.
Oh, I guess I can. Yeah, right. Yeah, the AV setup for this on Zoom is a little bit different than how I'd done it in my dry runs. So there we go. Okay, back to my mug. Okay, so the project is, again, a fairly standard Elixir application. At the top level of the application, there's a display, a movement, and a rotary encoder library. Display is responsible for managing the connection to the actual SSD to the OLED display. It tracks the face, so the face is basically that determines how we lay the text out and how to use the fonts. And it actually manages the physical connection to the actual physical device. It has a bunch of functionality for turning the display on and off, setting contrast on it, setting time zones, and actually updating the time. But the extent of it is about, what is this, 100 lines? There's really not much to it. It leans on this SSD 1322 library, which essentially I wrote as a quick little wrapper around the data sheet for this for this SSD, for this OLED display. And it essentially allows you to drive this with bitmaps. So if you looked at the display that I showed you, that's actually, it looks like text, but it's actually over the wire. It's actually just a bitmap, just a pixel map that goes over the wire to this device. And it provides a really simple API where you can say, at this coordinate on the screen, draw this bitmap that I'm going to pass you. And they're passed in as 4-bit grayscale bitmaps. So to actually build those bitmaps from text, there's this EXPaint library that I wrote that's a really thin wrapper around Erlang's built-in graphics device, the graphics device, I think it stands for, library. And this essentially just has a bunch of primitives built into it where you can draw rectangles, ellipses, text with simple bitmap fonts. And I've, on top of that, added some pluggable rasterizers so it can render out to PNG. It can render out to a few other formats, inline iTerm, which is kind of neat if you're an iTerm user, and also to that same 4-bit grayscale format that these devices use. It's really not terribly performant. It's literally about 50 lines that just wraps the EGD library in a tiny bit just to manage the state. I think this would be a really neat library to have sort of a very simple bit of graphics primitives in Elixir, but I don't really have time for it. But it'd be fun to build on. So coming back to the desktop library, right? That is essentially what builds these the actual display. There's also, as I mentioned, at an application, there's this movement module, and movement is essentially responsible. It is analogous to the movement in a watch, which essentially is the part of the watch which is responsible for keeping time, for making sure that the second hand moves, on a regular basis at the start of every second. So this is just a simple task with a very simple feedback loop that just kind of does a moving average based on how long it takes to draw the screen, and it adjusts when it calls the screen draw so that it completes the screen draw right at the 0 second crossing of the second, so that the updates come on a regular basis and they don't happen midway between the second. Last but not least, there's this rotary encoder, which is probably the best example in the project of how to actually use GPIO. So a rotary encoder, if no one's seen one before, I can't believe I don't have one handy, is this little, it's essentially a couple of switches that are attached to a little rotary device, and it clicks. You probably can't hear that, but it spins around forever. It doesn't have it's not limited. And basically it has two switches, it has two outputs on it such that if you read those in a certain way, you can read whether or not it's turning clockwise or turning counterclockwise. And it's also got an extra output that shows you when it acts like a button, and it just registers that as a button. And so this rotary encoder module is just a gen server that wraps a bit of state that goes and reads some GPIO pins that method of reading pins off of a rotary encoder is called quadrature encoding. So it just reads them off in standard quadrature encoding based on these pin numbers here, and then figures out which way the handle turned based on the particular values of the pins, and then calls display.setZone to actually set the time zone either to the next one or the previous one, depending on which way you turn it. So this is probably the best example of like straight up GPIO that's used in the project, as distinct from the SPI stuff that actually drives the display. So when you put all of this together, you end up with this clock that I think that I showed off earlier, which is actually fairly performant. It just sits there and does its job silently. I anticipate just keeping this thing on my desk for the rest of time and just having a clock that I can change, and I just always know it's the correct time. I also set the display up so that if it doesn't actually know the time, if it loses sync, it replaces the display and it says like cannot sync to NTP or something like that. So if it's actually telling you the incorrect time. And the nice thing about it, because it's, you can get fairly detailed and timely logging out of this, is how far out of whack you are. And it seems on average that this guy is usually within about 2 to 3, sometimes 5 milliseconds off from the absolute correct time. So, if you sat there with a high-speed camera and like a clock that you knew was correct, you'd be essentially neck and neck between this and that clock. It's about as accurate as you'd ever care to be in any case. So here's some links about the various places that I talked about, the NERDS project, how to actually get started with it, how to get started with doing GPIO circuit work, some places to go shopping, links to the desktop clock app if you wanted to take a look at what I believe to be a reasonably well-written NERVS app, fairly idiomatic in its approach to how to interact with these things, as well as the slides for this talk. Also, I'll mention if anybody ever wants to get into this stuff, wanting to buy the stuff locally, obviously you can buy these things off Amazon, circuit boards and LEDs and hook up wire and stuff. There's a decent shop on College Street called Creatron at like College and Bathurst area that sells a lot of this stuff. They deal a lot with U of T engineering students, so they kind of know what these random little projects look like. There's a Home Hardware across the street that also has some stuff across the street on College that has some decent stuff. There's also a Creatron location in, I think up in North York somewhere, I think on Finch or on Steeles, that they also have a location up there. So if you want to buy local, you want to just go and just see the kind of things that are available and the bits and bobs that you can tinker with, they're a good place to go locally to check that stuff out. So that's all I had to talk about. Happy to answer any questions. Happy to contribute contribute any discussions that we might have on the Toronto page, on the Toronto Slack, or if anybody has any questions now, happy to answer them.
Thanks, Matt. That was, as always, I gotta say, incredible. Thank you so much. Any questions?
I have a question. Matt, I'm just curious, why did you decide to create your own primitives library instead of using something like Scenic?
I actually looked at Scenic initially. The problem with Scenic is that I need really, if I recall, it's the rasterization step, which was the hard part, right? That was essentially being able to, take the output of this thing and then turn it into this really, I wouldn't even call it esoteric, but it's like a 4-bit, like packed byte streaming format that these devices use. So it was that step that I didn't really want to tinker with too much. And the other thing as well was that like I was doing all of this just to try to like get like I spent probably a week's worth of evenings in the basement here just trying to draw a simple like square on this device, and because there's obviously not a whole lot of like feedback with this, right? Like you're writing bits over a wire. So you do what you believe to be correct, you pour over the data sheet to try to figure out what, if you've got your timings right and everything, and then you hit run and nothing shows up on this, and you don't really have anywhere to go to debug it. Like there's not really any, first principles you can really appeal to. So it was, I was kind of trying to start with the simplest thing I possibly could. At one point, I actually hand coded a bitmap, like I just did a, 0xf0, 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 just to have like that would have been like a checkerboard, pixel by pixel checkerboard. And that's what I was actually throwing over the wire at this thing, just trying to be like, okay, if I do this and I'm doing this right, I expect to be able to look at this and see a checkerboard on the screen. And then there's a bunch of, not to get into the details of it, but this thing actually addresses the pixels from the center out on the board. So it's not even as really straightforward as having like starting in the upper corner and coming down. So that was a whole other, translation layer on top of Scenic that I didn't really want to have to deal with. It's essentially, the short version of it is that this stuff is kind of the layer below Scenic in a lot of ways. Where Scenic is good at compositing like widgets and stuff together and having like building like higher order control stuff on that. This is really just about how do you get pixels onto a screen. Does that make sense?
Yeah.
I mean, I would love to be able to integrate with Scenic. That would be a really, I think, a fun thing, especially for EX Paint. I think that would be a neat, sort of way to bridge those two together. This is about as, like I said, I kind of did this as a bit of a joke, an inside joke at work. And this is frankly, as far as I really want to take it at this point. There's too many other projects competing for my time, so.
I have a question more generally about nerves and working with hardware because I've never really done it. Obviously, I understand how you would test all of your Elixir specific stuff, like your tasks and your business logic, but how do you go about, I guess, like, if you were to test your clock stuff, would you just go mock those GPIO returns? I know it's going to turn to 0 or a 1, but from what I understand, some of those devices really aren't quite that reliable and stuff like that. Like, how do you deal with all of that basically?
Well, with one of these, for the most part, with a voltmeter, and you physically verify that what you expect is happening is happening. I also, like in a bunch of cases, like I'll actually just set up like you can. Like the buttons are a really good example, right? Input is in some ways easier because you can like absolutely tell what's happening You know, if I close the circuit, if I push the button on this guy, I absolutely know that that pin should be low. You know, and if I let it go, I absolutely know it should be high. So actually the circuits GPIO library is really fantastic. Like it's a really high quality piece of kit. And if memory serves, I think they actually have some support for stubbing on the host system. So the distinction in the embedded world is between targets and hosts, right? Hosts are the machine that you're compiling on, and targets are the machine that you're compiling for. Those are the terms of art for it. And I believe Circuits GPIO actually has fairly robust host support for that, for mocking those out. I mean, this being kind of a lark for me, I didn't exactly do TDD with this. There's no tests in the project. So I don't actually know is the short version of that, but eventually I'm going to use this to build, if you recall, the last talk I gave was about about Thousand Island, the socket server that I'm building. So the end goal of that is to build that HomeKit controlled IR blaster for controlling my air conditioner upstairs. So that I intend to, like, eventually I intend to host that on Nerves. So the end game here is to eventually have a HomeKit controlled Nerves machine that I can turn GPIO pins on and off with and blast IR codes out via HomeKit, and at that point essentially via Phoenix as well. So that's kind of like the long game with it. And at that point I'm going to be writing testing because there's a lot more to it. This was really just a way to win a bad bet at work more than anything else.
Oh man.
One thing I will notice for that too, though, if you look at the EXPaint, my EXPaint repo, in the README, and I think Tyler, you and I had a talk about this a while back in the Slack channel. You can actually you can render PNGs with that. You can render out to iTerm as well with it as well, which is really neat. You can actually do inline images with it that actually render inside iTerm if you're on Mac. So so you can, it's more generally usable for that. So certainly for a lot of the display for actually building out like the text on the display, a lot of that work I did just testing it, rendering out to PNGs or rendering out in the console. You know, just to be like, okay, I've got, you know, because there's some logic in the faces so that they don't, like, I don't redraw the entire face every time. Kind of much like LiveView does. Like if it goes from 0.2 to 0.3, I only really redraw the 3 on the second hands just for performance reasons. And so I essentially redraw the longest suffix of the time, which has changed since the last time I drew. And that's just a performance thing. So optimizing for that, I did most of that just in the console using EXPaint's render to console support. And then only then did I really punch it out to the hardware.
Very cool. Thanks, Matt.
All right. Well,
I have a question.
Go ahead, Max.
What were the specifics of the bet?
Okay, actually that's a good point. Now I get to plug work. So I work at a company in town called PhonoCloud. We do factory automation software. So we do, it's an on-premises, we essentially write software in Elixir to run automotive factories is the short version of it. And we're also hiring. One of the caveats of that is it's an on-premises solution. We have clients all over the world. So we're like, when we're diagnosing on-call issues, it's like we have clients all over the world, every time zone, and not every time zone, but many time zones. And, you know, it's just, we're constantly running into issues where like our log service is in, you know, UTC for some of us, but some of us have updated our settings so that it's in Eastern time, but then the plant might be in China. And is it daylight saving in China right now? China doesn't do daylight saving. Like time zones are a nightmare for us at work. And so as a consequence, everybody, you know, like we're often kind of like, you know, people have like the world clock web pages open up where they can figure out times in different places. So I had this gag about writing one of these for everybody's desk at work, where they could, you know, have UTC at the top, and then whatever, you know, machine they were on for, you know, for an on-call issue, they could just basically turn the dial until they were in China or until they were in Spain or, you know, Chicago, wherever, you know, wherever the plant happens to be. So that was really the gist of it. It was more of a, I think I can do this, and I'm going to do it and put one of these on everybody's desk, and you guys are going to have to use it because I made it just for you. So I ordered a pile of these things off Alibaba or AliExpress. I have like 8 of them in a box somewhere here to actually go and make these things for people. They're only like $10 each. They're ludicrously cheap. And so I was going to go and build a bunch of them, but like the joke's on me because I actually got really sick of just making one of these. I'm probably not going to make any more. So joke's on me.